Hi, my name is Alejandro Benitez. I'm a biochemistry junior here at CSU Channel Islands. I spent the past couple of weeks preparing for my Organic Chemistry 2 final. In the past 3 days, I have been filling up this workroom, so now I'm going to walk you through it and walk myself through it to make sure I understand everything, mechanisms, and reactions that I'm going to need to know for the final. So let's start with functional groups and naming. As you can see from here, I have a list of many different types of functional groups and their increasing priority. Basically, you just need to know that carboxylic acid has the highest priority and halide has the lowest. These names should be reviewed for you if you're in the course. So, carboxylic acid goes to oic acid, ester to O8, amide to amide, nitrile to nitrile, aldehyde to al, ketone to one, alcohol to ol, amine to amine, alkene to ene, alkyne to ine, alkane to ane. Of course, you name the functional group that has the highest priority, and then you name the substituents, putting them with the lowest numbering, and then alphabetizing. Now let's talk about some interesting functional groups. Now down here I have an oxyrane, but it's more commonly known as an epoxide. Up here we have a tosylate, which you could tell is a benzene ring attached to a methyl group and a sulfur attached to 3 oxygens. There's an anhydride, which is 2 carbonyl groups with an oxygen conjoining them as an ester. And there's an imine, and the difference between an imine and an enamine is the location of the double bonds. With an imine, you have it between the carbon and the nitrogen, and in the enamine, you have a nitrogen next to an alkene. Now, a gemdiol has 2 alcohols attached to a carbon with 2 alkyl groups, and an acetal has 2 esters attached to the carbon group. I'm sorry, not esters, ethers. And then a hemiacetal has an alcohol and an ether attached to a carbon, as well as an alkyl group and a hydrogen or another alkyl group. Now let's go over some basic mechanisms. So you have SN2, which is the most basic one, where you have which follows second order kinetics. K equals the Rx times the nucleophile, and it happens in one step where there's a backside attack of the nucleophile against the electrophile, which releases the leaving group, and you result in an inversion of configuration. Now unhindered halides react fastest, and that's pretty much all you need to remember about SN2. Now SN1 is a 2-step substitution mechanism, where first you have the loss of the leaving group in the rate determining step, which is slow, and you form a carbocation. At this point, you can have rearrangements to form a more stable carbocation, where you go from a first degree to a second or third degree. You then have the nucleophile come in and attack the carbon at the carbocation site, and then you have substitution. This follows first order kinetics, and you have a trigonal planar carbocation intermediate. The more substituted reaction happens fastest. Now let's go over elimination. Now you have an elimination in alpha and beta carbon, and you'll have a base come in and remove the hydrogen from the beta carbon, which is beta to the leaving group. By stealing the hydrogen, you put the electrons that were making that carbon-hydrogen bond and create an alkene. That alkene will then force the release of the leaving group, which will then result in an alkene, a water, and your leaving group. This is a second order reaction, and it's one step. Your more substituted halides react fastest, and it's favored by a strong acid. And a better leaving group which will give you a faster reaction, and it also prefers polar aprotic solvents. This again should be reviewed from your first semester organic chemistry. Let's go over E1. Okay, similar to SN1, you have the loss of your leaving group, forming a carbocation which can undergo rearrangements, and then you have your leaving group. You then have water, which comes in and steals the hydrogen from the beta carbon, which will then form a double bond between the beta and alpha carbon, giving you an alkene and an acid. Again, this is first order, and it has 2 steps, so the more substituted reaction reacts fastest. The rate goes from a more substituted carbocation to a least substituted carbocation with more hydrogens. And it's favored by weak bases from alcohol and water. The better the leaving group, for instance like bromine, the faster the reaction. And that's because the bond to the leaving group is partially broken in the rate determining step. And polar protic solvents that are the ionic intermediates are needed. Okay, so let's start with the reactions of alcohols. Dehydration, formation of alkyl halides and tosylates. Okay, so let's start with dehydration of second and third degree alcohols. So that's an E1 mechanism, and you have hydrosulfuric acid, which is going to give a hydrogen to this third degree alcohol, giving you HSO4 minus and an OH2, H2O on your alkyl group, which is a good leaving group. Then the carbon-oxygen bond is broken and releasing water, and then you have a carbocation which can undergo methyl or hydride shifts and water. And then you bring it back in the HSO4 minus and you find the beta hydrogen, remove it to recreate your catalyst H2SO4 and create a double bond between the alpha and beta carbons. Let's talk about dehydration. You have dehydration of a first degree alcohol, which is an E2 mechanism. In the first step, the oxygen is protonated again by H2SO4, and then you make water, which is a good leaving group, and HSO4 minus. The second step is that the carbon hydrogen and carbon oxygen bonds are broken and you form a pi bond. The HSO4 comes in and it steals the hydrogen from the beta carbon, which then donates its carbon hydrogen electrons to form an alkene in between the alpha and beta carbons. By doing this, you then release water, as it is a good leaving group and carbon already has 4 bonds. So then you have your alkene, your water, and your catalyst H2SO4. Up next is a 1,2 methyl shift during dehydration, which is what I was speaking about earlier. So the first and second step is you form a second degree carbocation. Again, H2SO4 comes in, it donates a hydrogen to the alcohol and it makes HSO4 minus. Then you have the water leave, and then you're left with a carbocation. As you could tell, it's connected to 2 other carbons, which makes it a second degree carbocation. The carbon next to it is a third degree carbocation, so you can then undergo a 1,2 methyl shift. So this is now a second degree carbocation, and then it becomes a third degree carbocation by moving that methyl group over. And then HSO4 minus comes back in and it steals the hydrogen, which donates its electron to make the alkene between the alpha and beta carbons, giving you an alkene. But you have 2 possibilities this time because you have 2 beta hydrogens. This time you can come in from the terminal beta and give an alkene on the outside of the product. Now, from what I was taught, an internal alkene is the more stable one, so that's the one more likely to be drawn. You will be given a mixture of products, but your top one is going to be the major product. Okay, let's talk about dehydration with some different reagents. Dehydration with POCl3 and pyrimidine. The first step is you're going to convert the hydroxide into a good leaving group. Now, your alcohol here is going to attach to the phosphorus, forcing one of the chlorines to leave from POCl3, giving you a complex over here of an alcohol attached to POCl2 with a positive bond. Pyridine, the benzene ring of 1 nitrogen instead and a double bond, is going to come and steal the hydrogen, which is going to donate its electrons back to oxygen to give it a neutral charge. And then you're left with the pyridine and the cyclic POCl3 ether complex. Then the carbon and hydrogen and the carbon-oxygen bonds breaks and you form a pi bond. So the pyridine is going to come back in, a different molecule of it, and steal the hydrogen from the carbon below the ether. This is then going to donate its electrons to form a double bond between the alpha and beta carbons, and in doing so you're going to release the oxygen POCl2 complex, giving you a product of a cyclic alkene, POCl2O-, and a positive pyrimidine. The next reaction we have is a first-degree alcohol with an alkyl halide, HX acid, which is SN2. Here, X can be chlorine or bromine. In the first step, the oxygen is protonated. It gains a hydrogen from the hydrobromic acid, and then the hydrogen-bromine bond donates its electrons to the bromine, giving you a CH3CH2 water complex plus bromine. And then you're going to bring the bromine back in, and it's going to do a backside attack of the carbon, giving it a substitution reaction. Then it's going to release water, which is a good leaving group, and you're left with CH3CH2Br and H2O. Now let's measure the same reaction, but this time we're going to use a second and third degree alcohol. Again, the first step, the oxygen is protonated, and the hydrogen is donated from HBr, and Br becomes Br-, and you're left again with a good leaving group and Br-. Then the carbon dioxide bond breaks, leaving a carbocation, and then bromine comes in with a backside attack, and you have substitution. You have to be careful with this one because whenever you make a carbocation, you can have rearrangements. The next reaction is going to be the reaction of an alcohol with SOCl2 and pyrimidine. This is an SN2 reaction. So first and second step, you're going to have the hydroxyl group on the alcohol convert into a good leaving group. You're going to do that by making the OH attack the sulfur on the SOCl2 and releasing one of the chlorine ions. You're then left with an ROH sulfur SOCl complex. Pyrimidine is going to come in and steal the hydrogen from the alcohol, which is going to then donate